when you're down in the lab, dialing in your laser powers and voxel
Oh,
size.
they tweak and everything.
Right, exactly. It's easy to feel like two-photon lithography is just this ultimate engineering flex. Like we're making the world's smallest, most precise shapes simply because we can.
Yeah, I mean, it kind of is a flex sometimes.
It totally is. But when that submicron precision solves a massive real-world medical bottleneck, I feel like the perspective totally shifts for us. So, welcome to this deep dive on the 2PP podcast. Today, we're looking at a really fascinating application of our field.
Very fascinating.
Right. Using laser stereolithography to actually fabricate a pumpless microneedle, and it's bioinspired by the Ligia exotica.
The sea Slater.
Yeah, exactly, the sea Slater. So we're diving into how 3D printing at this scale translates a weird biological mechanism into a practical device for diabetic patients.
And the translation from a rather strange crustacean anatomy to a medical device is just brilliant.
Yeah.
Because traditional minimally invasive microneedles have always been held back by the pump.
Right, the bulky hardware.
Exactly. You need these complex, bulky mechanical systems to draw the blood out. And even when engineers tried mimicking, like, hollow mosquito proboscises.
Oh, right, the mosquito needle.
Yeah, the physics just fought back. Because the thinner a closed needle gets, the higher the fluidic resistance climbs.
I mean, it's like struggling to pull a super thick milkshake through one of those tiny cocktail straws.
Oh, that's the worst.
Right, your cheeks are burning, but literally nothing moves.
Mm.
But the sea Slater entirely bypasses that closed tube fluidic resistance.
It does.
It naturally transports water up its legs using pure capillary force. And it does this through staggered microstructures that are located in completely open spaces.
Which is wild.
It really is. So it's less like that cocktail straw and more like a perfectly designed paper towel that just effortlessly wicks up a spill.
Exactly. But replicating that open space wicking mechanism, it requires resolving really complex, overhanging geometries without the structures collapsing.
Which is where our 2PP systems come in.
You guessed it. That's why the researchers relied on a nanoscribe photonic professional GT system. And they paired it with IPS photoresist.
Oh, IPS, nice. Good mechanical stability.
Right. It offers that high shape fidelity you need to print these unsupported 3x3 millimeter arrays. I mean, we're talking microstructures just 3 microns wide.
Wow.
Yeah, 3 microns wide, 25 microns high, and 25 microns long.
That is tiny. But mapping and printing arrays that intricate takes serious machine time. So I have to wonder, is fabricating complex, staggered patterns truly necessary? Like, why not just print simple, straight microchannels to pull the fluid up?
Well, the researchers actually tested that exact assumption, against the staggered design. With straight channels, the liquid rises initially, but then
This stops.
Yeah, the capillary pressure drops as the fluid column gets heavier. So the cohesive forces hit an equilibrium with gravity, the channel just saturates and the liquid sits there.
So no continuous flow.
Exactly. They even tested intermittent channels, so essentially dashed lines, but the gaps severely weaken the overall capillary force.
Okay, so the staggered geometry actually prevents that equilibrium.
Exactly.
The fluid must constantly be, like, reaching for the next closest edge. It acts almost like a microscopic zipper, continuously pulling the liquid upward because the overlapping walls constantly renew that capillary force.
That continuous renewal is the absolute key here. The walls of the adjacent staggered channels are positioned just close enough to maintain that strong pull without ever fully saturating.
That's so clever.
And to optimize that cohesive pull even further, they treated the 2PP printed surface with oxygen plasma for 80 seconds.
Oh, to make it hydrophilic.
Yes. That drove the contact angle down to 26 degrees, making the microgeometry incredibly hydrophilic.
Okay, but having the geometry perfectly wick fluid on a flat 3x3 millimeter plate is impressive, but, you can't exactly draw blood with a flat square.
No, you definitely cannot.
So to bridge the gap from a lab test to a functional biomedical prototype, they combined this 2PP printed open tank with a 650 micron glass capillary.
Right. And pushing red-colored water up a glass capillary is one thing, but whole blood.
Oh, yeah, the viscosity.
Yeah, whole blood introduces severe viscosity and immediate coagulation. If the blood clots inside those tiny 3-micron gaps, the capillary force dies instantly.
So did they have to, alter the printed geometry to account for the viscosity, or did they tackle the clotting chemically?
They went the chemical route. By dipping the assembled device in a 3.8% trisodium citrate solution, they prevented coagulation entirely.
Oh, wow. Just a simple dip.
Yep. That single, elegant adjustment allowed this completely pumpless open structure needle to collect exactly 0.3 microliters of blood.
Which, if I'm not mistaken, happens to be the precise volume required for standard diabetic glucose testing.
It is indeed.
That's incredible.
Yeah.
Our fabrication tools literally just eliminated the need for mechanical pumps entirely, simply by replicating a surface geometry at the microscale.
It really perfectly illustrates how two-photon lithography bridges the gap between pure biological observation and highly functional medical engineering. We aren't just making tiny shapes. We're fundamentally manipulating fluid dynamics.
It leaves you with a pretty wild thought, honestly. I mean, for everyone listening, if your two-photon lithography skills can perfectly replicate a sea slater's leg to eliminate mechanical pumps and blood drawing,
Right.
what other overlooked, totally bizarre microgeometries in nature are just waiting to be printed to solve our next massive engineering bottleneck?